Hello everyone, welcome to this lecture in the Machine Learning Teach by Doing series. Today we are going to learn everything about the convolutional neural network architecture. We have been preparing for this for the past two lectures. In the previous lecture we looked at max pooling layer, and in the lecture before that we looked at the filtering layer. Now we are ready to understand the entire convolutional neural network architecture and all the components which it contains. When you learn about CNNs or when you take any CNN course, you will typically see that this is the figure which they start with. And it's very difficult for students to understand because there are so many things going on here, and it's difficult to understand what really to um, or what exactly should I pay attention to over here in the first place. So let's see what all the different components are here. Here is the image. The image is that of a zebra. And then there are different things which are going on here. The first thing I want you to notice is that there is something which is written as convolution here. So convolution and convolution. This is nothing but the filtering layer. And we are going to revise what it means. Then there is a filtering layer, and then there is something called as the pooling. This is nothing but the max pooling layer. So first the filtering layer is applied, then the max pooling layer is applied, then again the filtering layer is applied, then again the max pooling layer is applied. Towards the end there is something called as the flatten layer, and finally there is the fully connected layer. So in terms of the components, if you look at the components, there is first is the filtering layer number one, second is the max pooling layer which is number two, third is the flatten layer which is number three, and fourth is the fully connected layer which is number four. There are some other things which are going on here which are related to the activation functions, but those cannot be really called as components because they have been borrowed from neural networks, and uh, I'll tell them what they mean. So there is this ReLU activation function over here, and there is a softmax activation function over here. So these are just non-linear transformations. For example, what the ReLU does is that it has, so ReLU of x is this: for x is less than 0, it is 0, and for x greater than 0, it's equal to x. So after we take the convolution operation, if some negative filter values are there, they are put to 0, and the positive filter values stay as it is, or the positive output values stay as it is, and the negative output values are put to 0. Softmax is needed because this is a classification problem. So if there are classes such as horse, zebra, and dog, and we want to classify among these three things, among these three animals, which one of these three animals does this image is closest to? So here if we see that horse is zero point 0.2, zebra is zero point 0.7, and dog is zero point 0.1, which means that there is 20% probability that it's a horse, 70% probability that it's a zebra, and 10% probability that it's a dog. So between this output layer and these probabilistic values, there is something called as the softmax layer. The main purpose of this lecture is to give a broad overview of these four building blocks: the filtering layer, the max pooling layer, the flatten layer, and the fully connected layer. Let's start understanding what each of these layers actually mean. This will be a revision based on the previous lecture, so it will be good to revise all of these concepts also. So whenever you see a filtering layer like this, remember what is happening is that we have an image over here, uh, and let's say that image typically has number of channels, right? So let me start out like this. So let's say this is a zebra image. This is a 4 by 4 image, let's say. And first what's done is that the filters are applied. The number of filters are decided. And so each filter, so let's say if the filter size is 2 by 2, this 2 by 2 filter is applied over this image, and then it convolves over this entire image, and it produces a 4 by 4 output. There are four filters over here. So it will produce a tensor which is 4 by 4 by 4. That's what a filter operation essentially does. So whenever you look at a filtering layer, ask yourself two questions. First, what is the size of the filter? In this case, it's 4 by 4. Second, how many filters I want to use. And here in this case, we are using 4 filters. Visually, let's see what this means. So let's say I have a coffee cup here, and I told you the filtering operation, right? So in this layer, I said the first question I ask is I want how many filters do I want? So I say that I want 10 filters: one, two, three, four, five, six, seven, 8, 9, and 10. Great. Second, what's the size of the filter? Let's say I want to 2 by 2 filter. Now let's see what the first filter does. When I go over to the first filter, you will see that it slides over this image and produces the output image. If I click over here, we can actually observe this operation in a lot more detail. So let me click on this image, and here you can see this operation. So let's say I have 10 filters, and let's say the size of the filter is 3 by 3, and then you can see I'm sliding over here right now with my cursor, and you can see that a corresponding output is being generated here. So you can see that every filter, so this is one filter convolves over this entire image and generates an output which is the same size of the image. So let me play this animation here. So here you can see now the animation is playing. Try looking at the filter as it is moving from left to right on the screen, and the output where it is moving. So this is what every filter does. Every filter does the convolution operation and produces the output as the same size of the image. What is really important is the number of filters, because the number of filters are going to determine the depth. For example, um, here I'm using 10 filters, right? Here I'm using 10 filters, and let's say if the input is 64 by 64, if I use 10 filters, it means the output is a tensor which is 64 by 64 by 10. That is the output of the filtering layer. So first, always decide the number of filters, and second, always decide the size of the filter. This is what is happening in a filtering layer. Let me try to explain this in the form of tensors. So let's say the output of one layer is 4 by 4 by 4, since there are 4 filters, and now you want to apply one more filtering layer. So first you decide the size of the filter, and this will be a 2 by 2 by 4 filter, because remember the input size is 4 by 4 by 4, so the filter also has to be a tensor. So the filter will be let me use orange color, and I'll erase this. So in this layer, let's say yeah, in this layer, let's say I'm going to use a filter which is 2 by 2, but I also need to convolve with the depth. So the filter also has to have the depth of 4. So the filter which I'm choosing here is 2 by 2 by 4. This filter will convolve over all of this tensor and produce an output which is 4 by 4. I also have to decide the number of filters. So if in this layer I'm going to use 10 filters, the output of each filter is 4 by 4, and I'm using 10 filters. So the resultant output will be 4 by 4 by 10. This is what is happening when you consider filtering layer. When you consider filtering layer, the number of filters are chosen, the size of each filter is chosen, and the output is determined. So whenever you look at a filtering layer like this, whenever you look at a filtering layer like this, I want you to imagine this visual here. So specifically, I want you to think of this visual over here on the right hand side of the screen, the animation which is playing. The filter is hovering, and then it is performing the convolution operation, and the output is being generated. This is exactly what is happening. And what is this filter doing? Every filter here is detecting some specific feature. So there are 10 filters here, right? Maybe this filter is determining the edges of this coffee. Maybe this filter is determining the curve shape of the handle. Maybe this filter is determining the liquid texture which is present in the coffee. So every filter here has a specific purpose, and when it's trained, it will do the task of identifying the particular feature. That's the advantage of the filtering layer. The filtering layer extracts features from the image which is fed to the filtering layer. Now, along with the understanding of the filtering layer, the nomenclature is also very important. There are three things actually which you need to fix. The number of filters we discussed about this, the size of the filters we discussed about this, but there is one more parameter which need to be fixed, and that's the stride. So when a filter operates on an image, always the output image won't be the same size as the input. If the stride is equal to 2, for example, when the filter operates, it will leave a gap of 1. So the output will be of the size of n by 2 multiplied by n by 2. So the stride actually determines the gap. If you want to reduce the size, you can always apply your filters with a stride, which means that if I do a convolution for this pixel, I will leave a gap, then I do for this pixel, then I'll do a gap. Then, which means I'm taking a stride of 2. A stride of 1 just means that there is the output will be the same as input. But if I have the stride of 2, it means the output will be n by 2 multiplied by n by 2. So it will scale down the image by a factor of 4. Also, one key thing to note is that the depth of the filter at the current layer is equal to the number of filters of the previous layer. Let's see what this means. When we were deciding the filter size, why did we choose 2 by 2 by 4? 2 by 2 can be 3 by 3, it can even be 4 by 4. But this third dimension has to be fixed because each filter has to convolve the depth of the input. And the input depth is the number of filters used in the previous layer, right? We use 4 filters here. That's why there is a channel depth of 4 over here. So this filter has to be 2 by 2 by 4. It cannot be 2 by 2 by 5 or 2 by 2 by 3 or 2 by 2 by 6, because this filter will be 2 by 2 and it will take the entire depth. So remember, the depth of the filter at the current layer is equal to the number of filters at the previous layer. So if the number of filter of the previous layer was ml, the size of the filter at the present layer will be kl by kl by ml. This has to be same as the number of filters in the previous layer. And let's say if the input is a tensor of size nl by 1, nl by 1 and ml by ml minus 1, the output tensor will be nl by ml. And if you are using a stride, nl will be equal to nl minus 1 divided by sl, where sl is the stride. If the stride is equal to 1, which means that the output dimensions will be the same as the input dimensions. Generally, the stride does not change the layer depth or the uh, channel size. So this means ml minus 1 will be equal to ml. Also, you might be thinking, when you consider filtering layer, what is it that we are exactly optimizing? Remember that there are no weights like in a traditional neural network. In fact, the weights are just the entries in our filters. So when we consider a filter, so let's say here we saw a filter, right? This filter. Yes. So when we saw this filter, every filter has a particular value which has been mentioned over here. So the 3 by 3 filters, it's a 3 by 3 filter, right? And it has a specific value. So those values are the weights of our convolutional neural network, which we will optimize when we do gradient descent and back propagation. So the weights are the entries in the filters, which we will optimize. This is the filtering layer. That is the first very important component of the CNN architecture. And I hope you have all understood this component now. The second important component is the max pooling layer. Max pooling layer actually has two attributes. The first is the size. In this case, let's say we want to do a max pooling of size 2 by 2. And the second is the stride. Generally, the stride is assumed to be same as the size dimension, so it is 2. So what this means is that I will have a filter, or I will have a filter which is, or just a matrix which is of the size 2 by 2, and with a stride 2, which means that I will split this input matrix into 4 blocks like this. And what max pooling does is that in each of these blocks it takes the maximum value. In the first block, the maximum value of this 4 is equal to 20, so here comes 20. In the second block, the maximum of these 4 values is 30, so here comes 30. In the third block, the maximum of these 4 values is 112, so here comes 112. And in the fourth block, the maximum of these 4 values is 37, so here comes 37. This is the output of the max pooling layer when this is the input. And why did we say stride is equal to 2? Because if stride was equal to 1, what would have happened is that this would be the first block, then this would be the second block, then this would be the third block. So the output dimension would have changed. That is also possible, but typically in max pooling, the stride is the same as the size. So stride equal to 2 means that we are leaving a space of 1. So the second block will be over here, third block will be over here, and fourth block will be over here. So the output is actually scaled down by a factor of 2 because we are using a stride of 2 over here. So remember that max pooling layer does two things. First is that it scales down the input. It's called downsizing, and that's one of the most important advantages of max pooling. It reduces the computational time. So for example, if you look at this layer here, whenever a max pooling layer is applied, you will see that the size is reducing. So look at the size here and look at the size here. This is of a lower size, right? These images, because a max pooling layer is applied. So remember that whenever a max pooling layer is applied, such as over here, the size is always reduced. And since the next layers operate on this reduced size, that overall saves the computational time in the convolutional neural network. This is one advantage of the max pooling layer. The second advantage is that since the max pooling layer only looks at the maximum value of the pixels in a given block, it extracts the most important features of the image and it filters out the irrelevant features. That's the second advantage. The third advantage of the max pooling layer, which not many people know about, is that it adds translational invariance, which means that it helps the neural network or it helps the CNN be less sensitive to small translations in the image. Let's take an example for this. So let's look at this triangle and let's look at this triangle. There is only a small rotation, right? Since max pooling only looks at the maximum value in a bunch of pixels, even if the triangle is rotated slightly, the output of the max pooling layer will always stay the same. Or even if the triangle is slightly rotated, since we are collecting a bunch of pixels and only looking at a maximum value like this, like what we saw over here, uh, max pooling layer actually adds this thing called translational invariance, which means that it helps the network be less sensitive to small translations, which is very advantageous to us. So there are three advantages of max pooling. It extracts most important features, it reduces the computational time, and third, it adds translational invariance. So this is the second important building block of the convolutional neural network architecture, that is max pooling. So let's say we add a filtering layer, max pooling, filtering, max pooling, filtering, max pooling. We do this for 5, 10 times. Then usually towards the end, there is one more layer called as the flattening layer. What this means is that let's say that we have reached at the last stage of the convolutional neural network architecture, and after the last max pooling we have an image which is 3 by 3 and with pixels like this. What the flattening does is that it just converts it into a flattened 9 by 1 vector. Instead of being it in a matrix, it just flattens it out. So that's the third component, which is the flattening layer. And the fourth component is the fully connected layer, which means that this flattened layer, let's say this is the flattened layer, and the output, let's say we are categorizing it into four outputs. Either it's a horse, or it's a zebra, or it's an elephant, or it's a dog. So these are my four output neurons, and then we again come back to neural networks in the last fully connected layer. So this is my flattened layer, this is my flattened layer output, and we saw the flattened layer as the previous building block, right? So the flattened layer output is then fed as a fully connected layer to the final four outputs, and then each there will be a weight matrix here. So every neuron here will have 9 weights and one bias. So this is like a neural network itself. And then softmax will be applied. And let's say the probabilities turn out to be zero point 0.1, zero point 0.6, zero point 0.2, and zero point 0.1. This means that it's 10% chance that it's a horse, 60% chance that it's a zebra, 20% chance that it's an elephant, and 10% chance that it's a dog. So this is the last component of the convolutional neural network architecture, which we can see over here also. So let me zoom in a bit for this last part. There is a flattened layer here, which is then passed to a fully connected layer, and then the final prediction is made, whether it's a horse, whether it's a zebra, or whether it's a dog. Our main goal here is to optimize all the parameters in this convolutional neural network so that the output values are correct, which means that we get the maximum percentage probability for the zebra. So what are the parameters which are optimized here? Of course, every filter which is used in the filter layer has weights associated with it. These are the first set of parameters. The pooling layer does not have any parameters, so there is nothing to optimize here. But the flatten layer also does not have any parameters. So the only layers or the only building blocks which have parameters are the filtering layer and the fully connected layer. The fully connected layer has weights and biases, and the filtering layer has weights associated with each filter. So this is the combined set of parameters which we need to optimize so that the output of this convolutional neural network is correct for the input images which are fed to it. And this is how the convolutional neural network architecture is defined and it is trained. So just to summarize, the parameters to be optimized are the filter weights. So in the filtering layer, every filter will have weights, and there might be multiple filtering layers. And then the final fully connected layer also has weights associated with it. So even those will need to be optimized. And you might be wondering, how are these optimized? Very simple. They'll be optimized through back propagation and gradient descent, which is exactly the same optimization routine which we actually saw when we optimized the weights and biases of a normal neural network. So this was so just to summarize, there are four building blocks in a convolutional neural network. The first building block is the filtering layer. The second building block is the max pooling layer. The third building block is the flatten layer. And the fourth building block is the fully connected layer. These blocks are arranged together. Out of these four blocks, only two blocks have parameters which need to be optimized: the filter layer, and then finally the fully connected layer. Okay, so this actually brings us to the end of this lecture, in which we saw the convolutional neural network or CNN architecture in a lot of detail. Now, whenever you look at a CNN diagram like this, and you might be seeing many such diagrams on the internet, whenever you Google, let's say, CNN architecture, a diagram will come which looks like this. So let's say you look at the first diagram. Now you should not be intimidated by it, because you know the building blocks. You know what it means when you see the convolution. You know what it means when you see the max pooling. You know what it means when you see the flattened over here. And you know what it means when you see the fully connected. All convolutional neural networks essentially have these four building blocks. And I want you to write these building blocks so that you are not afraid of them and you understand them a lot better. um, Many big companies and researchers now use pre-built convolutional neural networks which have already predetermined architecture which is working the best for them. And not many changes are made to some of the best working architectures. This is because if an architecture is working well, it means the filters are detecting many different things in the input images, and those same filters can be used for a new task. And that is also sometimes called transfer learning, which means that we use the existing architecture, make some changes, and then use it for a new problem. As always, I'm trying to make these lecture series as visual as possible, and I write down everything in front of you. These are my handwritten notes so that you feel connected to what I'm trying to learn and what I'm trying to teach over here. However, it's very important that after this lecture, you also write down whatever I'm showing here. The goal is to show that CNN are not that difficult. It's just that these images might look a bit complex at first, but if you break it down into building blocks, then everything seems easier. Thank you so much, everyone, and I look forward to seeing you in the next lecture.